who know an awful lot about quantum. And then after that, there's also a display on quantum. And without commenting on what it means about quantum, I think the visualization of what quantum is over there is pretty cool. So take it away.
Okay, great. Thanks so much. Really honored to be here. I was going to start with quick intros, but we've already done that, so I guess we can just dive right in. So I will ask Elizabeth to start by saying, let's begin at the beginning. What is a quantum computer?
That is a good question to start with. So a quantum computer is a fundamentally new and different type of computing hardware that takes advantage of certain quantum physics principles that allows us to process and store information in a different way. The way that we're able to do that helps us then solve problems that we currently cannot today, even with the best and most powerful AI and classical computing tools that you heard about this morning and will probably continue to hear about. An example of how this could happen is, so there are different ways a quantum computer can be built, but they're all based on something called a qubit, and a qubit is a quantum bit. They are different than classical bits of information, which is how we currently store and process information, where a classical bit could be either a 0 or a 1, and that represents certain information, where a quantum bit can be a 0 and a 1 simultaneously due to a quantum physics principle called superposition. And this is an example of a principle that allows us to just store and process information in a fundamentally different way and sort of unlock a new paradigm of computing and allow us to solve problems in a different way and new and different problems. Quantum computing is still in the early R&D stages, so we at Google, as well as many other players in the space, are working towards building a large-scale quantum computer that's capable of tackling these big, impactful problems. As an industry, I say the focus is probably improving the quality and scaling the size of these systems that we have today. The systems we have today, you can kind of think about as like small prototype level devices. There's a lot of work to address all the technical and operational and policy challenges ahead to get to this point of these large-scale quantum computers. Our mission at Google Quantum AI is specific to Google, of course, but it's to build best-in-class quantum computing for otherwise unsolvable problems. I say that just because it's sort of encompasses all the components it takes to achieve a goal like this. So building an actual quantum computer means all of the hardware development, actually building a new hardware system, then the software that runs on top of it, and then the algorithms and applications that we use the quantum computer for. So like I said, there's a lot of work ahead, but it's all towards this mission that we believe to be super, super impactful and again, allow us to solve problems that we cannot today.
Thank you. Yeah, I always like to mention that we don't know exactly what quantum computers will be useful for in the long term, but they will probably be pretty special purpose devices. I think it's very unlikely that anyone in this room will ever use a quantum computer to run Microsoft Word or check your email, but who knows? But there's some problems that they can solve, some computational problems they can solve much, much, much faster than existing computers. But realistically, there are a lot of other problems that they won't be able to solve any faster because, as Elizabeth mentioned, there's a lot of huge hardware overheads. These computers tend to run a little bit slower than regular computers. So it's still very much a work in progress as to exactly what they'll be used for, which leads me to my next question, which is, what are the kinds of applications that we might expect from a quantum computer in the near and then longer term?
Yeah.
So I thought,
oh, sorry.
sorry, I thought I might actually give kind of my very high-level perspective, and then you are free to, correct, add, supplement, tell me if I got anything wrong. So again, still a matter of active research, but I think there's a few categories of kind of commercially useful, socially positive potential applications that seem promising for quantum. I think the strongest case for a near-term application is probably scientific simulation. So there's a lot of different versions of that, but basically we're talking about modeling microscopic systems that themselves use quantum physics. So that could be things like biochemistry, materials science, solid-state physics, chemistry, and there's really a large number of potential useful applications of that, everything from drug design to the design of new materials to improved chemical processes. People talk about fertilizer production a lot, making that cheaper and more widely accessible. I mean, you can imagine sort of no end of useful applications of better understanding of chemistry, things like better batteries, better solar panels, better lightweight structural materials, kind of, the possibilities are pretty much endless. I think the second kind of big picture category of what quantum might be useful for is sort of optimization, machine learning of big data sets. I think there the picture is a little bit more complicated. There's certain algorithms that can give kind of a relatively modest speed up for a huge class of problems. There are a few other more specialized algorithms that can give an enormous speed up, but for a narrower class of problems. So it's kind of a complicated trade space, and I personally think we'll probably need to actually build some more advanced prototypes and play around with them to really understand exactly what they will be used for. And then the third category of applications is a little more concerning, perhaps, which is one thing that we do know quantum computers may eventually be really good at, is factoring large numbers, which may seem a bit esoteric, but it turns out that all the cryptography that is currently used to protect internet traffic relies on the difficulty of factoring large numbers and closely related mathematical problems, which means that if a very large, mature, advanced quantum computer were to be dropped down on Earth right now, that could actually be very concerning because whoever was running that computer might be able to essentially read everyone's internet traffic, everyone's email, everyone's online transactions, all the credit card information that's being passed to Amazon, all the sensitive corporate R&D, even classified national security information, uses this encryption, which is currently vulnerable. So that's kind of the flip side of quantum computing, the dark side, if you will. And there are solutions to that, but it is something that we should kind of think about how to roll out countermeasures responsibly in tandem with the technical advancements going on with quantum computing themselves. So that was a bit of a monologue, but does that all sound right to you? Is there anything you'd like to add?
Yeah, no, that was very well said. I'd say like our general thesis around the future of quantum applications is pretty similar to what you just said. It's basically like quantum computers will be a powerful tool for computation for solving certain types of problems. So there are certain like problem areas in which we see quantum computers having this significant advantage compared to classical computing, including like the best AI. So this idea of quantum simulation is one that we talk about often. It's basically like there are certain materials, chemicals, molecules that we can just better understand using a quantum computer that then has applications in things like battery design, drug discovery, solar cells, industrial catalysts, and so on. There are other classes of problems like quantum machine learning, optimization, differential equations, unstructured search, these sort of like research problem areas. And of course, one of which being factorization. So again, like our current digital security relies on the fact that it's really hard to do factorization, but a quantum computer finds it a bit more easy and then can solve factorization in something we call Shor's algorithm far more easily and faster. So we basically have to plan for, in a post-quantum world, we can no longer rely on factorization and Shor's algorithm in the way that we do today. So again, like keeping that in mind as we plan our progress and path forward, making sure we're keeping that as part of our plan forward, of course.
So given that quantum computing is kind of a dual-use technology, you might say, there are these potentially extremely positive, commercially valuable applications, also some riskier ones. How do you see this tension kind of playing out as quantum computers actually go out into the world? Like, which class of applications do you think will be ready first? The sort of safer ones or the more risky ones? Do you think we'll have a long period where this is kind of a straightforwardly positive contribution and then the risks emerge, or will it be kind of thought of as a dual-use technology right from the very beginning?
Yeah, that's a good question. I think we kind of see that playing out right now, even though we only have like these smaller prototype level devices, like similar to how we talk about AI, there are sort of riskier scenarios versus like hugely beneficial scenarios. And I think the way that we're approaching it and sort of see it going forward is sort of mitigate the risks of the risky situations as much as you can as early as possible with the most urgency involved there. So on this cryptography piece, that involves like making sure that we have set post-quantum cryptography standards and making sure that businesses, governments are transitioning to these post-quantum standards so that they are no longer at risk to this future quantum computer that can break the current encryption, basically making sure that we have new encryption that is, can exist in a world where there are quantum computers. And if that is the case, then you can sort of innovate as rapidly as you need to in order to stay competitive in the field, and also make sure that there is not another nation state that's trying to get there before us. So I think like mitigating the risky situations as early as possible is, of course, key. So it allows us to innovate on the applications that we find to be most impactful.
Yeah, I think there's kind of an interesting contrast between quantum computing and AI. They're often compared for clear reasons. You know, they're both very high technologies and similar uncertainties about the high impacts. But I think there's kind of a difference myself, which is AI, there's great uncertainty, as we heard in the previous talk, about kind of both the upside and the downside risks. It's just really difficult to predict what that will look like. With quantum, I think there's uncertainty in the sort of positive risk, although we certainly have stronger scientific evidence than we do in the case of AI. But the sort of negative risk is actually quite well understood. I mean, we know the risk. We don't know when the quantum computers will actually be able to take advantage of that risk, but we know the solutions. We have pretty sophisticated estimates of what size of a quantum computer would be needed. So I would say there's kind of generally less uncertainty on the risks. I mean, certainly still many large unknowns, but there's also a pretty clear path toward mitigating those unknowns. There's a couple different options for countermeasures against the risk to cryptography. One of them Elizabeth mentioned, post-quantum cryptography, which is like a new set of math problems which sort of work the same way as our current cryptography, but with the big benefit that they are not believed to be vulnerable to a quantum computer. So once we move over to these new like algorithmic methods of doing cryptography, the risk, as far as we know, is essentially eliminated. So how would you say the rollout of this post-quantum cryptography is going? Are you kind of comfortable with the pace of implementation?
Comfortable would be a strong word, but I think the U.S. has done a really good job of kind of like what you said, identifying the risk area and creating solutions before the actual risk even exists. I mean, so for sort of context, we're at the scale of maybe 100 qubits in our systems. We'll need about, we estimate, 1 million qubits before this encryption risk is real. So we're still a ways away from that being, a risk in the real world, but it takes a long time to develop these standards and then also replace our current standards with these new standards. So the US government has done a really good job of developing these PQC standards through NIST. They've had sort of like a competition-based forum where we've developed these new encryption standards for years now. There's been executive orders to demand that the US government transition to these new standards by certain timelines to make sure that those timelines are prior to when we have these 1 million qubits so that we are safe before that point. So I think the US government has done a good job of creating the solutions and setting the timelines. We as industry